So, good morning everyone. This presentation will be given by Bart the Clerck about a very interesting subject in the MaxEntropyGraphs, a library, if I'm correct. And Bart has an engineering background, and nowadays I focus on network science and AI applications for intelligence. Good luck.
Hi. Oh, that's a bit strong, maybe. Morning, everybody. So indeed, I'm Bart. I'm from Belgium, Brussels. I have two affiliations currently, so I'm wrapping up my PhD at Ghent University in Belgium, and I am also working as a teaching assistant in the military academy, which kind of explains the intelligence take to my talk or in my presentation. So here you have the title. This is my GitHub profile. If you want to try this for yourself or just follow along, you scan this, you end up at the repository which contains this Pluto notebook. So I'll be discussing graphs in a sense, because I'm not sure to what extent everybody here is familiar with graphs. I'll just briefly show you what the package I'll be showing here covers, for now at least. So we have three different kinds of graphs you can work with. These can be the most basic type, just binary graphs without a direction on it. They can be directed, where you can have one way, well, going to, coming from, or a bidirectional edge between nodes. And we can also work with bipartite graphs, where you see two colors in the nodes. And this is typically used to represent something in a network model, where the two colors of nodes match with very different things. If I'm link this to social media, for example, this could be, the blue ones could be users, and the red things or the red dots could match with web pages they are sharing, right? So that's one way these things can be used. So that's for graphs, and that brings me to the next part, which is random graphs, right? Why do we use random graphs? Well, this is a topic that has been around for decades, actually. So, and what I'm be focusing on is maximum entropy graphs, which is a subtype of this. So, how do you get random graphs? Well, you take a real world. Yeah, I'll see if that works out. Well, that's maybe a bit excessive. Is that okay for you? Right. Okay. So what are these random graphs? Well, you have observed something in the real world that you can represent as a network. You impose some constraints on this. Typically, what you often see is you fix the degree sequence of each node, because you can only observe parts of your graph. And then you shuffle this around in a way or another, right? And all of these possible options you have of shuffling your graph around eventually leads to probability distribution, so the sum of all your graphs and their probability should add up to 1. There are two, and these are very conceptually different approaches onto doing this. So if you have your graph and its constraints, you can either impose them as hard constraints, meaning that every graph in the ensemble you will generate will match the specific constraints, or you can impose them on average. Which is this representation here. And this is also the framework that is being done or used in the setting of maximum entropy graphs. Well, why might you want to do this? Well, for example, if you make a measurement error because you observed something but not everything, well, if you're one measure off, the soft constraints still allow for other less strict adherence to the constraints you imposed. So that kind of works out. So what is this maximum entropy principle? Well, this exists, well, in general in information theory, and you can also apply these to ensembles of graphs. So basically the problem you want to solve is you want to maximize the entropy of your ensemble subject to a set of constraints. So up to now I have not specified what these constraints should be. I just gave you an example of degrees that you impose for each node. And that's basically a very generic framework you can use for graph randomization. And then depending on the type of constraint you will impose, well, you will come to a different model, you will have some likelihood maximizing parameters you need to determine. And if you know these, well, then you can start doing some prediction or some inference. So if you know these parameters, we can generate our ensemble. And then we can compute, and that's where things become relevant for us. You can compute either for a metric x on your graph or on your ensemble. You can compute its expected value, the variance, but you can also start doing sampling on ensemble. And oftentimes sampling is also a very useful thing that we want to do. So why use this? I think that's maybe most interesting question to ask. This has been used in many, many domains. Has been around in biology. If you want to look at food webs, for example, how different species interact, do we see some patterns that occur there that can explain for some structures in the way species interact with one another. This has been used in economics as well. That was how I came into contact, conceptually at least, with the methods. If you look at the exchanges between banks over time, like I think it was even the Dutch interbanking network, if you see how that evolves over time, following these approach. There were 3 years preceding the 28 financial crisis, there were actually indicators in the global system that something was off, right? Obviously this was done a posteriori, but nevertheless, still an interesting observation. What else? Well, and this is the way I use it mostly in my day-to-day research, is validated projections of a bipartite graph. We'll get to that later on, but basically what this allows you to do is to take a very large graph and filter out and only keep the interactions that are actually relevant for you or the thing you are studying. Okay. So, architecture-wise, doesn't this already exist? Well, yes, it does. However, the M word was mentioned during one of the main topics. So obviously here you have the license being a big issue. This is not open and free to use for everybody. And what is available to do these types of analyses? Well, documentation is often lacking. And as I mentioned, you will often use these to generate random graphs. So you will need to sample from an ensemble. And then the way you obtain the sample, that varies between approaches. If you do it here with MATLAB with available tools, you get an adjacency matrix. Okay, fine. It can definitely be used to represent the graph. If you do it in Python, well, you will get an edge list as a txt file. And whereas if you use it in Julia, you get out of the box, you will just get a graph, which is great. Also, the day-to-day analysis capabilities, both here and here to some extent, is an issue. For those of you who are working with Python, I think you can very much adhere to this meme in the middle. I've experienced this myself in the week preparing for this, because as you may know, NumPy 2.0 came out 1 or 2 weeks ago, and that was a breaking change. So I had to force myself in the package, the dependency lists for the current packages to use something below 2.0. Okay, it's fun, but you need to know how to fix it. Additionally, in the solvers we had there, well, although the methods used to solve the optimization problems work, they were like do-it-yourself, so not depending on existing high quality and reviewed packages. Same for the statistical analysis part. This works in Python, it's performant. However, it's already cheating a bit in the sense that it uses Python, but also Numba to have a JIT compiler. It uses Cython because, yeah, C is faster, obviously. Then you also need to bring in another graph package, which may or may not generate compatibility issues. So all these things add up and lead to frustration at one point. Additionally, well, gradients can be hard-coded, Hessians can be hard-coded, great, but the more complex your problem gets, the easier it becomes to have errors here, right? And different people at one point as contributors have said here in some of the Pythons, hey, by the way, there's an error in your gradient. Okay, good. If you use autodiff, less of an issue. Okay, another reason to use Julia. So eventually, to some extent out of frustration, this led me to build a package for myself to do this in Julia. First of all, well, because it wasn't available yet. The whole thing is native Julia. I can use the Julia package manager, which just works out of the box. I can use Documenter. It integrates perfectly with the JuliaGraphs ecosystem. So if I sample a graph, whatever the underlying model may be from my ensemble, the result is the proper graph in the JuliaGraphs ecosystem. I no longer have to pass through edge lists which I need to import, etc. Because it is Julia, I can use the existing high-quality numerical solvers that exist within the ecosystem. And from experience, this has led to better convergence. So a couple of models which did never converge due to the complexity or the size in Python could be solved with Julia. Great. An additional pet peeve of mine was the lack of a standardized API. Depending on the model you used, sampling or projecting had a different syntax. Frustrating. So kind of smoothen that out and just standardized API. It was mentioned this morning as well a couple of times. It's so easy to do multi-threading within Julia. And additionally, you can leverage Julia diff, the entire ecosystem, if you need gradients of whatever for entire functions the user can define themselves. And that just works out of the box. It's almost magic, but it's just great to use. Okay, so that's the reason why. Then just to show you how this entire thing is stitched together, well, basically the center of everything is a model, which is a subtype of an abstract max entropy model. Then you have a couple of submodels that are defined in there. This interacts with the numerical solvers, which can either be NL-solve or optimization. It extends some of the methods of JuliaGraphs. It extends some of the randomization functions we have, works with distributions. Also because there's statistics involved, it interacts with multiple testing, which is just works out of the box, and a couple of metrics have been defined in the package that work for both classical graphs but also for the ensembles. To make things speedy, or as speedy as possible with my skill sets, we use buffers wherever we can to avoid allocation issues, which is a very big showstopper in Python implementations. And also there are a couple of single-use functions. So to speed up those things, I've leaned upon pre-compile tools, which makes things easier for these single-use functions. Right, so how do you use it? How does it work? Again, quick check font size, is that okay? Or you can maybe up it just once. Right, so if you're working with an undirected graph, people who have done something with graphs at one point in their life, the Zachary Karate Club graph is maybe a well-known thing. Right, so basically a social network of a karate club that had a sort of a dispute, then had two very distinct groups. Well, this is just, you define the graph. This is JuliaGraphs. This is just graphs.jl, nothing new. You can generate a model from this. So the UBCM, that's just one of the different models that exists within the package. You can solve the model to obtain the likelihood maximizing parameters, and then you can just generate a random sample, in this case of 1,000 graphs following this specific model. Alright, so you saw the time, the first one was 4 seconds. This just takes me 11 milliseconds to generate this. So that's nice. To keep things light, because these are all small, if you go at larger scale, there's one downside, I'd say, of using these models, is that the adjacency matrix of any of these models just gives you a probability of a connection. So by default, it is dense. Right, so there's very little gains you can make by making it sparse. And so by default, these are not computed. However, you can ask to compute the expected adjacency matrix. You can compute the variance of each element in your adjacency matrix. And then once you have those, well, you can actually start building or doing some statistical tests. Like for example, you want to check if there is a degree assortativity in your graph. What does this mean? Well, do nodes with a high degree tend to connect with other nodes with a high degree? And one way of quantifying this is a metric called the average nearest neighbor degree. Literally, its description is in its name. So you can compute the degree for each node. You can see what was observed in your graph. So this will be my reference value. And then I can also compute this metric for my entire sample. And then you can just visually see, how does this look like? Well, if you look at the plot, well, you have a somewhat of a decreasing tendency, so you have a disassociative behavior. And if you look at the plots, so the distributions, the box plots, these are the values for each computed node, and the ones shown in red are those that are statistical outliers, if you want, right? So that's more or less what we obtain here. And that's just for a simple directed graph. If you want to go beyond, I mentioned biology a couple of times already. What is often done is look at motifs. So subgraphs of some type that occur more or much less than what you would expect by default. Let's say, so a couple of these food webs are available in the package as well. And syntax-wise, you'll see it's very similar to what we just did. Right, so I define my graph, just a big bay food web. I define my model. This time it's a directed model because the edges go both ways. I solve it, I generate a sample, and then from this specific sample I can see, well, is it a anomaly or not? If need be, well, again, you can compute the expected adjacency matrices and their variance. And now, how do I need to, can I do my statistical analyses? Well, I pick a metric function. So here it's just called x to be very generic. I can get my estimate either from the ensemble directly, or I can compute it from the sample as well. Right, you see I have the distinction between x hat e, so this is computed on the ensemble, or I get an estimate from my sample of 1,000 graphs. And this again leads me to do a statistical analysis, and here nothing seems out of order, let's say. All right, final thing, or final approach is bipartite graphs. So on the left you have a bipartite graph, and you can project these on one of the two layers. So here in the middle we have projected our graph on the U layer. So basically you want two nodes here are connected if you can reach them. And the right one is the same thing, but for the V nodes. Okay, and then what you might want to see is there a more substantial number of interactions between two users than what you would expect again under some null model. What you can do here, for example, it's a crime network, and then what you would have, well, the nodes would be criminals or actors, and the other group of nodes would be the crimes as such. And then you could see, well, are there any criminals that are often connected through a specific crime? And if so, what are those? Well, again, you can define a bipartite network from this. This can be projected, so this is implemented by default as well. If you want to do this projection, this works for a bipartite network by default. Again, standardized syntax. I want to generate a new model, solve the model, and I can also get my filtered network. So again, this is the same syntax again. This just takes the original graph and this projects the model. So here, my statistical validation is already included. And then you can get a small message that just shows you, well, hey, for this specific network, 86% of the edges was significant for the persons aspect, and 83 for the crime aspect. All right, so that's just a quick overview of the functionalities. And then I also have a quick word on performance. So I used both benchmark tools and the PyTest framework to compare with its closest competitor. So these are the specifications of what was run. Yes, I know this is not the latest version, but okay. Assume it will only become faster. Whoops. And a small thing that is relevant, I think, in terms of performance, is when you do the computation of the likelihood maximizing parameters for these types of models, is that it is not the size of the graph that is determining the complexity of the problem, but is the number of unique constraints or pairs of constraints. Right, so that can make something very easy or very difficult to compute. Right, if you have a star-like network with 1 million nodes, you only have 2 constraints because there are only 2 unique degrees. Then just some plots from performance-wise. So these are for the undirected network model, while just instantiating an object. There is some orders of magnitude in difference in computation time. Okay, but that's just instantiation. But what is maybe more relevant is how fast it is to compute the parameters. So the brown, let's say, is the competitor, blue is the Julia implementation, and overall, for the most used approach, fixed point method in general is the fastest, and for almost all models will work fine. Massively more rapid, and then also there's the decrease, well, the divergence increases as the size goes up. So that's a good thing, let's say, for us. One thing you might notice, or for the skeptics among us, well, indeed, my little star here, my Newton method, is slower, sorry, and even much slower. Well, the only reason that this is there is that this was computed using autodiff for the Hessians, which makes it a lot more numerically expensive to do. Right, so that's the reason why it is slower there. For the directed network, this has trends in the same direction. And then for the bipartite network, or the bipartite configuration model, and the BiCM, what I looked at here was computation time, because this is something I had to do in my own research activities, but typically for quite large networks. And that took so long, using default Python implementations, I was somewhat frustrated. I was like, hey, couldn't this be faster? Well, yes, it turns out it can. So each symbol in my graph is a specific method. There are two ways you can do the statistical validation. I won't go into detail, but the general tendency is that it is still, well, Julia is also faster, or orders of magnitude faster for doing this as well. Okay. So that performance, I'm more or less out of time. How do I want to proceed with this? Well, there are some more optimizations that could be done. I would like to add more maximum entropy models in general, because it's a very broad family of domains that also work for like hypergraphs and multi-layer graphs and so forth. And I also like to try out to what extent Julia GPU could be used to accelerate things more. Right, and if you have any tips or suggestions, please reach out. Also, the GitHub for the project is available. There is a documentation that shows you how it works, how to install. So if you have any questions on that, feel free to reach out. Yeah, and if you have any questions now,
Thank you.
I'll be happy to take them.
Are there any questions? Okay. Hey. Give the microphone to you.
Hi, thanks for the talk. You said that for one of the optimization methods, the computation of the Hessian was very expensive, I think.
Yeah.
Could it be that the Hessian is sparse and that you can leverage that sparsity in autodiff?
You could, however, for these types of models, unfortunately, it is very dense. So yeah, I tried playing around with that, but it actually made things worse than better.
Are there any other questions? No hands? 7 minutes left. Thank you.
Yeah, stupid question maybe, but I don't fully understand what happens when you take the karate club graph, for example. What does it do when you call solve? How does it get statistical information from that, or is it already in the source data?
No, just by calling solve, what you have, what you obtain are the parameters that define the ensemble of your random networks having that constraints matching your original network. And it's then from there you can either analyze your statistical anomaly both from the ensemble perspective by computing it right on the ensemble, or by looking at it from a sampling perspective. And depending on the size of the graph, again, because we need to keep the full adjacency matrix in memory, which is dense, you will either work with the ensemble if it's small enough, or use a sampling-based approach, which will be much faster when doing it for larger networks.
Thanks.
Any other questions? We still have 6 minutes.
Yeah, so the question is why do we consider specifically this family of graph randomization? Well, it is true that there are a lot of randomization algorithms and approaches that exists. There are multiple reasons. This works quite well at scale, which was the issue we were trying to tackle at the time, because social networks, when studying those, they unfortunately tend to be very large. And so using something like ergm from R, for example, is not really suited to run this at scale. Additionally, they also allow for errors, and because you don't strictly impose the constraints, you can just look at a distribution, and for everything that's based on a real-world observation, well, it's my belief it's always better to allow for some natural variability instead of just imposing hard constraints. But it could also be like in biology, or for if you have some underlying reason, it could very well be that you need another randomization model. But for now, there are not so many available in Julia, in the JuliaGraphs ecosystem. So there's also some room for work or collaboration there as well, I think.
Okay, thank you very much. Thank you for your presentation and time. So we have a bit of time left, but I think a round of applause will be in order.
Thank you.